Today we're at the NASA Glenn Research Center. We'll be talking about some of the lessons from a master practitioner, Dr. Rafat Ansari. In many cases, what we do is we focus on the management of missions or the engineering or technologies. This, to me, is a particularly exciting discussion that we'll have since Dr. Ansari is a leading scientist conducting a lot of breakthrough science that leads to many technologies that have an impact not only in space and for astronauts, but also on the ground in terms of Earth. Since 1988, Rafat has worked at NASA to advance light scattering technology for space experiments on board the Space Shuttle Orbiter and the International Space Station. And these have had applications for new technologies in the biomedical area for citizens and for people in terms of health. In his efforts, he's been involved in monitoring the health of astronauts who are involved in long-duration missions. He's developed methods to diagnose diseases non-invasively and quantitatively before clinical symptoms appear, using light in various forms to detect ocular and systemic abnormalities. He's been involved in developing fiber optic sensors to evaluate ocular tissues, and on Earth, the techniques have been beneficial in developing early detection of conditions that indicate the possibility of cataracts, diabetes, macular degeneration, Alzheimer's, glaucoma, and other potential illnesses. Dr. Ansari has just finished a 3-year study on laser-induced retinal injuries that has been funded by the U.S. Air Force. He's currently also involved in conducting citizen science in terms of studies on water quality and the algal bloom, monitoring the nation's waterways in support of the NIH. He's been involved and won many awards, and his work has been described as paradigm shifting in terms of the impact, in terms of the work that's taken place. So it's very exciting for us to talk with you, Rafat. And I was able to visit your laboratory yesterday, and that added to a lot of the excitement. And so what I'd like to start with is you're a scientist, you work with your science at NASA through projects. How did you get started in the research that you're doing now? What got you to NASA, and what got you excited about doing science that's having these kind of implications?
Well, thank you very much, Ed, for having me on your show today, and thank you for visiting the lab yesterday. And I think that was a great visit, which prompted to bring a few things for the demonstration here today. So in answering your question about how did I get to NASA is a pretty interesting story. And my NASA journey really started very, very long time ago, okay, 1962, when John Glenn flew the first mission. And my first mentor was my father, who really brought me to into education about space and those type of things. He would bring home Life magazine, black and white pictures of all the space program that I grew up with. And then in 1969, when the moon landing occurred, at that time my goal was to really go into physics and learn something that someday I might go just to see the Saturn V rocket. And that was just the dream to come here. So in 1984, I was able to go to a conference in Florida, which my supervisor sent me when I was finishing up my PhD. And I saw an experiment which was flown on the space shuttle at the time on Columbia. It was to do with Lehigh University experiment in growing polystyrene latex spheres, and the experiment called emulsion polymerization. And I was to some degree involved with those type of experiments in the lab I was doing and applying laser light scattering to look at what you get at. So I came back and told my supervisor about the experiment, and I said it would be really nice to do some light scattering on this thing. And then that led me to leave the PhD program, finished my degree, and then went to work and went to another conference in Atlanta in 1986. And someone who was sitting in the audience there was a professor from Cleveland. He invited me to give a seminar here. I come here. And in the passing, I mentioned that experiment. And they said, well, are you available to go to dinner tonight? And I said, yes, I am. And then we met, and they said, there is a NASA center over here in Cleveland. And I said, I don't know. There is a NASA center really in Cleveland? They said, yes. I always thought NASA is in Houston or in California, in Florida. So that led me to come here finally. And I started off doing working in the ATD area, which is the Advanced Technology Development Project, where my job was to really, along with another team members, to reduce the size of about almost say a 2-3 tables, full tables, optical tables, into a very, very small size, about a shoebox size. And then you could take it up on the shuttle and do experiments in fluid physics, experiments in the protein crystal growth experiments, material science experiment that I was involved with in zeolite materials experiments, those type of things, and so on and so forth. And once we got there, then finally, I switched on to some medical application that you mentioned in your introduction. Right. We can talk about it.
And we'll get into, so people can see, we'll get into examples. So you one of the things you did is that you clearly worked through different people, through universities, to come to NASA. You were impacted. We spoke yesterday about the fact that in talking to and learning from, you had different mentors, you've worked with different people, you continue that. What was the early advice? Was there anything that you were told early in terms of your career that really had an impact that you would recommend for others to learn from? What had a big impact on you and what people told you when you first started?
Okay, well, the first thing I would say that I still remember my supervisor, PhD supervisor, Ross Hallett, the day I received my PhD degree. Okay, so normally what happens when you finish your exam, they ask you to leave the room, and then you normally bring it back, and if they say, congratulations, Dr. So-and-so, that means you passed the exam. Okay, so I got in, and they said exactly the same thing. I said, well, thank you very much. And my professor said, Rafat, this is not just a certificate to practice science, but it is a certificate for continued learning. It's a lifetime learning. And imagine this, so that is stuck in my mind forever. And second thing happened was that when I got my pilot license, pilot certificate, a few years later, my instructor told me exactly the same thing. He said, the only thing which know how to fly are birds, and we are not birds. They are the true aviators. So this certificate that you got today is a lifelong learning that you have to do. And I'll tell you that until this day, I'm flying very frequently, and yet every flight is different, and you learn from your experiences. In terms of mentoring, I think the whole NASA here, when I came, really adopted me as one of theirs, absolutely. And how many people that I worked with, I'm absolutely blessed to have their advice, their mentorship, my branch chiefs. Okay, in fact, one of them is sitting in the audience, Dr. Singh, and he has been my mentor for 23 years. To this day, I go to these people, ask them about some advice or some of the things, and they are very, very helpful. Okay? And later on, when we talk about ophthalmology, the field of ophthalmology really adopted me to this day. And they have taught me so much that I have really been blessed with all of these people working with.
Yeah, and so one of the things that came through, again, we were together yesterday, which was wonderful. It's amazing to me, it's amazing the career you've had, in addition to the successes and obviously the talent that you bring. You've done so many different things. It was like there's a different story, and it makes me think about that example you had of keep learning. That you obviously made a decision. You weren't going to just get good at something and stay there. You seem to you work with groups. You work on problems. You see different potential applications that then lead to different work. And so you have a comfort level. It seems to go into different areas. Is that and that maybe that's also part of your collaboration with other teams and other organizations and entities.
Yes, indeed. Collaboration is a big part of it. Okay, and from the individual side of things, or from the programs or the NASA policies and stuff like that, you have this program that you have to fit in what you're doing. How does it benefit your agency? Okay, number one. Number two is that we, as scientists or as physicists or engineers, we are really trained to solve problems. So you see problems, and from those problems, you would see another problem. And one thing which humbles me all the time, and I think I'm really talking about other scientists as well, that how little we really know, how much that we do not know. Okay. And one thing that I would mention, that when I come into NASA every morning, and you look at Brook Park Road and NASA Parkway intersection, there are two huge signs, one on the east side, one on the west side. The east side says research and technology, and the west side says for the benefit of all. And that's what really inspires me, because when you are here at this wonderful, amazing place, there's so much that you can do, not just for NASA, not just for the work that you have had, but you can also identify and look at other problems and bring that into, and that's where collaboration begins. Right. Because when I work with scientists in, say, biochemists or medical doctors, I do not know everything about it. So those are the folks which are really instrumental in taking this from here. So what I refer to as bench side to bedside. So all the research that I have been doing so far is called translational research. So I'm translating it into real practical applications, and that's what I really love doing it.
It also seems, in listening to you and spending time with you, it'd be very easy for you to have a sense that you're expert at everything. And sometimes when people get at that point, they stop listening to others. They're giving, or they protect their. How did you? I mean, one of the things that it seems like you're involved in is that you're sharing your knowledge. You're studying things, you're exploring things, you teach. You mentioned yesterday you go to different conferences. It seems like you work with different communities. I've had people tell me sometimes they're afraid to share their wisdom or their expertise because once it gets out there, it's less value. You don't seem to have any worry about that. Can you talk to you? Why are you comfortable with sharing? What makes you so excellent? Does that help you in terms of your?
Because
what's your thoughts on that?
When I share something with someone else, I learn from them. Okay, because they continuously, you ask. So give you a couple examples. So for instance, there was some time back that I was doing an experiment, and I was looking into the tissue in the back of the eye, which is called vitreous. And I did not know what I'm really looking at. Okay, I was getting some data, it was looking very good. Okay, and now when I submitted an abstract, I thought I will go ahead and present this abstract and say, this is what I was looking at. And of course, we have to have some science, solid science behind it. And I have no idea what I'm really looking at. So I went to this ophthalmology conference, and I'm very nervous. But I got there on the podium, presented it, and at the end I suggested the following. If anyone out there in the audience who could guide me and make me understand what exactly I am looking here at. Of course, it's fluid, this is what I'm looking, few things I know, but I don't know how to interpret these results. And as I'm walking down, they called another speaker to address the conference, and he's coming in, he looked at me, and he said, we need to talk. And then I sat down, and he started talking. He referred to my talk, and he said, this is what the ophthalmology needs, what Dr. Ansari just presented. It is absolutely amazing because I have never seen anything like this. And they started explaining. And right there, the two of us just connected. I did not know who he was. We found out he was one of the most famous ophthalmologists in the world. Okay. He's in California. His name is Jerry Sabag. He's an absolutely amazing guy. He has written 3 books on the vitreous. Okay. One of the books came out 914 pages long. And if you look at this fluid I'm talking about, is only 300 microliters. Okay. And on that, there's entire world hidden in there that you can look for diabetic retinopathy, for diabetes, for other diseases. So this is how you learn. So if I'm shy and say, I don't know, well, if I don't know, I will tell you that I do not know. Let's discuss this. You'll come to the conclusion. So that's what I normally do.
You have a comfort level in terms of when you see something, it doesn't make sense to you, where maybe other people would keep that quiet and not say, hey, I don't understand these results here. And then you're comfortable to go to a larger audience. I guess they can even, they just call it, crowdsourcing or looking for answers, but saying, hey, these are the results, I'm not sure, does anyone have thoughts on that? And then the ability to work with others and collaborate, you obviously feel has been a large part of of the success that you've had?
I do believe strongly that do not just think that you are the expert of anything, because I'm not expert of anything. And for that matter, I'm not really a jack of all trade either. Okay? But we do whatever we can, okay, to understand. And the problem with the scientists is that you go and resolve problems. That's what we do. Sometimes we are successful, sometimes we are not. But in the process, you obviously learn something new.
Right. So want to get into actually some of the research. So when I was, we're in the lab yesterday, one of the things I saw on the wall was obviously a paper that was blown up, which was along the lines of basically the eyes are the window to the body. Now we've heard the quote, the eyes are the window to the soul.
Right.
And it's the eyes are the window to the body, which is a great. I mean, it reminds you of everything. Is basically your research is about the use of light and laser to non-invasively look at the eyes, and from that to be able to predict way ahead of time the health of people.
Right.
And maybe you can talk about that, how you got started, and maybe you gave an example to me. You said put your eye into one of these areas and you look at it and it's a light in there and it's blue, and then you can see different movements. You explain that. So maybe you can talk about the importance of the eye and then for the applications it has for the research you do.
Okay, sure, I will be happy to. So the demonstration that I gave you yesterday, that eye is indeed a window into the body. Okay. And before I go there, I would like to say you also interjected the discussion on light.
Yes.
Okay. So now it is really interesting to see this. For the past 70,000 years of human life or human existence, the humans, once the sun sets, only dependent on one source of light, and that was the oil lamp. Nothing more, nothing less. Okay, that's it. And then the first light bulb was invented by Thomas Edison, okay, incandescent light bulb, in late 1800. Okay, so about 150 years old. And that's the light bulb we came in all the way until in 1960s, when the lasers came in. Right. Up until that time, there were no lasers, nothing. So theoretical papers were written, like such as Raman scattering. Dr. C.V. Raman, who was a professor in India in 1926, he received the Nobel Prize. Okay. Nobody really knew how to use this invention. Okay. But after the lasers came in, all that stuff came to life. So now go to 1990s. Up until 1990s, there were no LEDs. Okay. Fiber optics came in. So all this communication advances in light technology, and now you can see they're all over the place. It just completely revolutionized the world that we live in. So now, rather than going and opening and dissecting things to see what is happening inside the body, we can use the power of light to put inside the body, in this case inside the eye. And the reason is because when you look into the eye, normal eye, it's all transparent. So you go in the cornea, behind it is a fluid called aqueous, behind that is the iris, and behind that is the lens, which is also transparent, and behind that lens is the vitreous, and behind that is the retina. Every tissue type and every fluid type that you see in the eye represent every tissue type and every fluid type in the human body. So if you are shooting light because it's transparent and you are looking at these morphological changes from cornea to the retina, then you are really assessing disease at a very early level. And when you say early level, I'm talking about the molecular level. Okay? And only light can do that. So the reason that you talk about that paradigm shift
Right.
before, I just want to mention that is because now we are able to do invisible tissues, making them visible. And that's what the American Ophthalmological Society and the ophthalmic community tells me, that this is paradigm shift because you are making invisible visible now.
Right. And it's non-invasive.
It's completely
So
non-invasive.
again, when you first said put your head in there, I'm
Yes.
kind of wondering where am I going, but it's
That is
there's
correct.
no, and it's I would assume it has to be cheaper because you're not operating. You're able to look, through through the techniques you've come up with.
Yes. So, for example, if you're going to say, well, is it MRI, okay,
Right.
imaging or something like that, or OCT imaging? These are wonderful technologies, absolutely great, but they only look at structural changes. Right. We are looking at molecular changes. That's what the difference is. Okay, and then cheaper. Well, what does it cost for a LED? Okay, it's cheap LEDs. Fiber optic cables are not very expensive. Of course, you have to have computers with it, you have to have other electronic gadgets there, and then you do it. But when you produce these things at a mass level, then they are very, very cheap. Compare the television of yesterday to the computer television today. I think everyone now almost have a television in every room, right?
Or
Before
on the phone.
on the phone.
Yeah.
Okay, all of that stuff.
Yeah.
So that's a very important aspect of technology development, because now we are using what other folks have done in engineering and in industry, that we can absorb that into medical technologies.
So we have some examples. I don't know, is there a place that you would start in terms of explaining to me, in terms of some of your research, what it's done in terms of the models or the prototypes?
Yes, I will be happy to do that. And so first example, I mentioned to you about the eye model right here. So
Right.
this is the eye model right here, okay? Yeah. And everybody knows this is a camera, right? And eye is built as a camera. The nature has done that job for us beautifully, okay? It's just like a camera. So what the camera does, it takes light in. So here, thank you for holding it.
Yeah.
So if I take this piece out, say take that out.
Right.
So this is the cornea right here. That's the cornea. Very transparent, has the highest refractive power of any tissue in the body. And that's what we make it, us to focus light and stuff like that. And then you take this thing out, and behind that, right here is the iris. And this level here, this chamber is filled with a liquid or fluid, just like water. And that is called aqueous humor. Aqueous is like an ultrafiltrate of blood, serum. So all the blood that we have in our bodies, consider that to be an ultrafiltrate right over here. But all the molecules that your blood shows, so for example, you go for blood chemistry.
Yep.
Okay, you want to look for cholesterol, you want to look for sugar levels, okay, for diabetes. You can look right here,
Right.
okay? By shooting light, taking it off, you can tell what's going on in there. Right. And
So
also,
the chemicals that would be in any part of your body.
that's
you
right.
can
That
see
will show up
easily
here as well.
through the eye.
That is correct. Second thing is, when you're looking at the aqueous, now you'll take a look at the inflammatory responses. Okay, you get cold,
Yep.
your eyes are red shot. Those are the introduction of proteins in this level over here. And then you got the iris, which obviously closes or opens depending upon the outside light in there. Okay, and behind that is this lens that we have. Okay.
Oh, I
And
thought
this
I
is
saw
the
M&Ms
lens.
in there.
Right, that's the lens. Now this lens over here in the human body is of the size of an aspirin pill. Okay, very small, about 4 millimeters in diameter. That's what that is. Okay, this is a highest amount of arrangement of crystallins in there. It's called protein crystallins. Right. And the amount of protein in this lens is 35%, which is the highest concentration in anywhere else in the human body. That is this lens.
And so what's the implication of that?
So the implication is that the nature has built this in a beautiful way.
Yep.
That this transparent. So it focuses
Okay.
the light right here behind the retina,
Yep.
right over here, okay? And that's how we see it.
Okay.
Okay. But this thing here, and this is what our research have shown, that can tell about initial stages of other things which are going wrong in the human body,
Right.
like oxidative stress, which is responsible for aging. And we'll talk about aging, and when astronauts fly in space, this is
Right.
what John Glenn used to say, okay, that the space travel accelerates the aging process. And you can see that aging process right over here in this tissue, okay? And then behind of that is this. This is that vitreous, which is 98% of the globe here. And this gives the structure. It has collagen, it has fluid in there, which is hyaluronan and water. And that really changes both in aging as well as in physiological changes. For example, if this person is diabetic,
Right.
the diabetes have shown big effect on there. And behind all that is the retina, which makes us see things. Okay, it's like the film behind the camera. That's what this one is. And then this is optic nerve right over here, and that connects with our brain, okay, which interprets what we are really seeing. So within this retinal vessels here, it is another interesting fact about the retina. It is the highest metabolic object in the body. That means it consumes tons and tons of oxygen, okay, heavy duty. And that's where the diabetes is very dangerous in the body, because it started to reduce that. It acts more and more because the basal membrane has started to get damaged. And then new vessels start to form in the retina in the forward direction here to the eye, in the anterior direction, and that start to leak fluid or blood. Right. And that is diabetic retinopathy, which has no cure right now, only that can be managed. Okay.
So all different aspects of the eye seem to be very early indicators.
That is correct.
Of the health.
That is correct. Okay, things which are happening other places,
right.
but you can see it over here.
Yeah.
Okay, high blood pressure, for example, leads to glaucoma. Mm-hmm. Okay, and radiation effects leads to cataract. Radiation effects lead to age-related macular degeneration. Yeah. Okay, so those are the kind of things that it happens here. So this is why we say eye is a window to the body. Right. Okay, by looking at this. Okay.
It also seems like it would be accessible. So you work on research for astronauts. They're going to be in space.
Right.
I'm assuming you can then have cameras, but even before that, you want to, explore so you can be predictive of people's health.
Yes. So that's a great question. So in fact, we might have gone through that a little bit later, but let me explain that for a second. So for example, in normal aging, let's talk about normal aging. Right. Okay. Normal aging, when you have this lens, and we are growing old, okay, older and older. So what happened? Right now, 40 years and above people in United States, there are about 22 million of us who have some form of cataract. And in 2030, that number is going to become 44 million. Okay? 19 million surgeries are done everywhere in the entire world. 5 million surgeries alone in the United States. Okay? Now, we are very lucky because we have great training and great trained doctors and everything else, so the risk factor for these kind of surgeries is very low. But in the developing world, that's not the case. Okay? It is higher level of risk factor and stuff like that. So that's the effect of aging. And we say, well, how do we protect that? Okay, well, there could be people smoking, people exposed to radiation and stuff like that. So when the Fukushima disaster happened, then the NIH, National Eye Institute, and National Institute of Health requested us to send our device to Japan to look at people who are exposed to that. Now, the similar stuff is happening also to astronauts. Okay. So here on Earth, we are exposed to, say, ultraviolet radiation mostly. So whatever you see out there today, and if you go to Mars today, that number will be about 800 times higher for ultraviolet. There are 3 types of ultraviolet radiation, ultraviolet A, B, and C, okay, UVA, UVB, UVC. UVC is absorbed normally by the atmosphere, but UVA and UVB create havoc in the eye tissues. Okay. So think about, we are standing on Mars right now, 800 times that what you have over there. How to mitigate that effect, this one. But when you are on Mars or in space, there is major issues with other type of radiation. And that is the cosmic radiation, the solar wind, okay, which has high ionizing radiation, and that what give the damage to the DNA, and then the whole thing starts to affect. Okay. So with that,
and so I'm gathering it. So these are different tools or prototypes that you're using for different ways of understanding the eye and therefore health. Is that?
Yes, indeed. So for example, this development here, which used to be a very large, apparatus equipment, this is the optical component of that. Okay. So you can just hook up one little tiny laser, very similar to a laser pen kind of thing. Okay, and then you can just shoot the light in one of these guys here, and shoot it right. Just set it up, just like that. Okay, in a equipment that we set it up. And then you can take the light back, put through your computer, and you can tell very early onset of not cataract, but how the protein molecules are being affected.
Right.
Okay, because cataract by definition is the opacity of the lens. Okay, so there is no opacity right now, and that was the big thing that we discovered. So what we discovered now is what called alpha-kiristin index. And I was really challenged by Rick Ferris, Dr. Rick Ferris, over at NIH, to come up with something that they don't want to have physicists to tell them all mathematics behind it and the physics behind it. They want to know one single parameter that they can associate with patients and how are these people doing.
So they have a problem.
Yes.
And they want basically a way of diagnosing it, assessing it, or understanding it.
That is correct. That is correct. And they also have provided us, their power of, biostatistician there and the clinician there, Dr. Datilas, and Suzanne Vitelli, and with whom we worked on with this thing. So now.
And how do you, large part of what you're doing is collaboration. You're coming up with innovations.
Yes.
Creative ideas. Tell us a little bit of how does something like that happen? What's the innovation? How do you work that? Did you?
Well, when we scientists work in the laboratory or think about it, we don't really think in terms of that. Oh, I'm going to go to the lab today. I'm going to innovate something.
Right.
Okay. It doesn't happen that way.
Right.
Okay.
So how does it happen?
And okay, you fail. You try something else, and then you have something at the end. In this case, we were successful that we got something very small, very power efficient, and all this stuff, because we just tried to see, well, what kind of sources we can use, what type of detectors we can use, what type of fibers we can use, and then how can we put this in an arrangement where it has higher signal to noise ratios and stuff like that. So that what the innovation comes in.
So you have a problem
Yes.
that needs to be solved, and sounds like you do a lot of experiments, try different things
Absolutely.
out. And this looks good, and then you go through a testing and and all that. So
Yes.
that for you is the innovation.
It is.
approach.
So when I mentioned that research and technology, which is written back there on the NASA
Right.
entrance, okay, so that is the research component of that.
Yeah.
Technology component is this,
Right.
but they go both hand in hand.
And
okay,
then
you
the
have to have
sharing
knowledge.
is for all, the
Abs-
benefit of all.
Absolutely.
So
You
it
put it
comes- yeah.
better than I can do.
Uh-oh. I'm learning. Yeah.
Thank you.
So, and one of the things I'll say is, we have an audience here, so if we have questions, we'll start collecting that and doing that. And so you shared this with me yesterday.
Yes.
What would be an example of?
Okay. So this is really an interesting project. So a couple friends of mine who were the NASA astronaut doctors, or what they call them as flight surgeons.
Right.
Okay. So these flight surgeons were talking to me one time, and they suggested that there is pretty high level of ultraviolet radiation on the space station on the shuttle, and they showed me a photograph of one of the astronauts who flew in space. And when they looked outside the window, then other than this area here, their entire face was very red. Okay, so they got a sunburn. They said, okay, well, you have no idea, how much light is really coming through it. And I said, well, it's perhaps true that you have, this space station, so they have to be shielding in there of some sort. He said, well, but how did they get the sunburn? Okay. So do you have something that
How
we
would they
can
know
take a look at? Right?
that's
How
happening?
much is that?
Yeah.
So that prompted me to work with a couple of students, okay, and then these students, I gave them this project and asked them to make a device, because there are devices available commercially, and we said, can we measure UVA, UVB, and UVC all simultaneously, because no one has done its simultaneous measurements yet.
Right.
So they made this sensor here works on a 9-volt battery right here, okay,
Right.
and then this, if you push this button, it goes 30 feet away to your computer,
Yeah.
and you can just wear this very simply, just like that, and now you can have a device which measures the exposure to these 3 type of UV radiation, how they are coming in and affecting
amazing.
your eyes. So that's what this one is for.
That's,
Sure, you can try
I
it too.
can try it on.
Is it comfortable?
Wow, it's cartoons. Yeah, it's very comfortable.
And imagine the cost of this thing. 9-volt battery,
Right.
$5 glasses, okay, and nothing to it. Okay, so it's
Right.
pretty this is a simple device.
There you go. That's amazing. Getting a picture taken with the strange devices.
Well,
And
there's-
so one of the things you also mentioned, so you have a lot of students that you work with.
yes,
And the
sure.
students are at universities, and so is that also a feeder for you? What do you gain from working with the students? With their, they're learning about what you're working on. What's the does that add to the interest? Does that make it more fun? Do they bring different perspectives?
Oh, absolutely. They bring different perspective. I learn a lot, from the young folks. In fact, one of them is sitting right over there, Peter. And you do. So what happens is that their preparation, for example, the people who did this work, they came from Italy, okay, the Japanese student. And when you do science, it really goes beyond the national boundaries. Okay, there you can talk about different cultures, yes, but it goes beyond the national boundaries. Because scientific culture, no matter where you go, is the same. It's about discovery, and it's about sharing the knowledge and creating new knowledge. So these guys have beautiful understanding of electronics, circuitry and stuff like that. So when I sat down with them and I told them that this is what my vision is, this is what I like to achieve. Could you do this thing? Okay, and then we start the process, okay, going through the literature, looking at certain things, what they are, and that's how we came up with this device.
Yeah, you've made a lot of connections. One of the things that's clear to me, you love working with people.
Sure.
All different people, and you had mentioned when we first got together that you were actually in a course, that I did 1989 or something, and it was around managing with people.
Yes.
And
so
even then, you saw the nature of the relationship.
Absolutely. So 1989, that was my first course here at the lab, okay. And I even forgot that who gave it, but when I saw you yesterday, I thought I've taken this course from you, okay, that's why I mentioned to you. And the name of the course was How to Work with People. And I think that was a great course. And the reason was that when we work, we always think about ourselves. But what you taught in that course was that when you're in a team environment, when you have people to work with, never think that they are working for you. I never think that my students are working for me in my lab. Okay? We are all working together. And in that respect, I have to say this, that seasoned managers here at this place are wonderful in that regard. I have not seen yet maybe one or two, but not seen anybody else who said that I'm your boss, okay, or you are working for me. Okay, we are working together. The agency is the same. We are all working for the common goals. So that what really inspires me.
Yeah. No,
so your course was great too.
But I mean, you're like a scientific rock star. People tell me, oh, how excited they are to hear from you, work with you, collaborate with you. But I can hear from the stories that get into the collaboration or that initial dinner that led to a career, or the curiosity you have. It navigates itself off of the things that you learn, the questions you have, and then an active interaction and play and learning with other people. So it comes through.
Absolutely.
Why don't we sit down? We have some questions.
Okay.
From the audience, but this is when we were at originally we weren't going to have any models, but when we were having such a wonderful time, I said you have to bring some of these. It gives great examples. So one of the questions we have from our audience here is, how widely used are these diagnostic technologies in public health care? So are they used beyond astronauts? Are they starting to be used for the larger population? And I guess that also gets to a core NASA question of, you'll get asked the question, why are we spending money in terms of space or research or NASA? And this gets into the issue of how does it impact the day-to-day lives of people? So are the technologies starting to be used?
Okay, so that's a very, very good question. And one of the things that I talked about with this oxidative stress and cataract has been used in some very major studies. Okay, so what you're talking about there is the one study that we did in 2011. And that was the study on several hundred patients, and that was done at the National Eye Institute. Okay. Now, one thing that you have to understand, that whenever you come with something new in medical area, the validation process is a very long process, okay, because they would not allow you to use it in humans immediately. You have to validate the whole thing, okay. The process, you have to show all that stuff. So it takes time. So we did a very major cross-sectional study, which came out very nice, and on that, the 2011 Department of Human Health and Services, it acknowledged us with that study. And then after that, subsequently, we did longitudinal studies. One longitudinal study was done at Johns Hopkins, one was at NIH, one is just about to get published from Japan. Okay, so we did 3 more than. And they are all correlating very, very well into these things. So as time goes on now, okay, people will be utilizing it. Now, another big aspect of this is that up until now, we were doing it for research and for exploration. Now we are at a point where some of the biochemists looking at the potential of this, and now they've already started working on some dogs and some animals to bring drugs to discovery. Okay? And now this could be used for looking at different drugs. Could that mitigate the risk of this aging or this radiation or something is happening? How could we protect people? So for example, if suppose you could delay the onset of this cataract by say 10 years, then people will not have to go through surgery for age 90 or 95 or something like that. So it's going to be a very major effect of that. So that's what I think.
Yeah, so it's a major implication of the research you're doing, which has obviously direct benefit for space and for astronauts, but for the health of people in terms of predicting and analyzing. Another question we have is, you mentioned the laser study for the Air Force. Can you discuss a little bit about that and some of the findings from the 3-year study?
Okay, sure. So one of the things is that when you look at the US Air Force interest in the laser-induced injury, we all know that you are not supposed to look directly into the laser. Okay, we all know. So for example, I have this laser pointer right over here, right? And then we say, well, laser pointers are safe. Okay, I mean, I can just shoot this right over here. This is very low power indeed, right over here. It's not burning my hand, but still, I'm not supposed to look directly into the beam or a scattered beam.
You shouldn't take it and point it at people in the
yes,
audience.
I will not do that. Okay, I mean, I can do it right over here that you could see right there. Okay, but that's about it. So these days, the military is seeing rise in retinal injuries. What this does is that when it hits the retina, it creates a retinal lesion in there, okay, which could be very dangerous. People can go blind, okay, if not immediately, a little bit later. So the idea was the Air Force came in and they said, well, can you build something that we can see this damage, if there is any, very early on? Okay, because in the battlefield, there is level 1, level 2, level 3, level 4 evacuations. Can we use something which is so easy to use in level 1 evacuations by the time the person goes or get some effect? Some of these injuries are painless, okay, because there are no really pain receptors in the retina, so you don't even feel like it. So how do you see it? So we came up with hypothesis along with the medical doctors, my co-investigators on this thing and team, that if there is an inflammatory response in the retina as a result of this exposure, could some protein molecules would rush to that injury and try to help alleviate it. But what is the probability that some of these protein molecules can enter into the vitreous, okay, in the front, and can we measure that? So that's what the project was. Now this project also affects the American people. How does it? So if you look at the incident these days, every single day in the United States of America, about 18 to 20 people, pilots, get this laser, not injury, but laser incident every single day. So what's going on there? So when the plane is coming to land, okay, it has an angle like this. It's about 1,000 foot for AGL. That's always the case when they're coming on final. And they're coming in, it takes a jet airplane only less than a minute to land to the airport. And the most difficult aspect of flying is landing and takeoffs. All accidents happen during that time, especially landing is a very tough thing. And if you are shining this laser in the pilot's eyes, okay, not necessarily they will go blind with this thing, but it distracts them. So it's a very, very big safety issue. So we came up from that angle and said, okay, well, let's see if we can see it. So with 3-year study we did in animal models, not in humans yet. Right. The results came out very well. So my colleagues over in Akron and Johns Hopkins, They did the animal study, and they also did the proteomics analysis. So for example, by taking the lens, the vitreous out of these eyes, and then taking it to the lab and doing all kind of chemical analyses, you would see those proteins, but not non-invasively. So what we did is give a handle as a non-invasive diagnostic for doing it. So now obviously in the future, perhaps this might go and help people in the field or otherwise.
I guess I'm thinking you're saying 18 to 20
hits every day.
pilots.
That's correct.
And that's from people.
People shooting the laser incident, not 18 to 20 pilots. Yeah,
Okay.
That what is right.
Another question, one of the other studies we talked about was the algal bloom,
Yes.
which a lot of people have read about, the growth in algae and the issues there. What's the nature of the research that you've been doing, and what are you learning from that?
So this is not something that I'm trained for, or I have done anything in that regard before. So 2014 was the year. In fact, I would go to 2011. I was flying with my wife over Lake Erie here,
Right.
in the Western Basin, and the water was very green looking down there. It was really very bad. And then she indicated to me that the water looking like this. So I said, well, what is that? So we don't know. It looks almost like a paint. Somebody put a paint in there. So we landed at our airport, and from there we were going for dinner anyway. There was a nice Mexican restaurant by the beach, so we went there. And the smell was horrible. Okay, if you look at that, there were also big signs on the beach saying that it's not safe to go in water. But we forgot about it, didn't pay much attention. And then here, in fact, in this room right here, in 2014, 2013 later, there was a conference, and I was asked to give a talk on something else. Okay, so while I was doing it, the other guy came in and he gave a talk on algal bloom. Okay, so NASA Glenn Research Center has a very robust program in monitoring algal bloom. Dr. John Lakey is the person who is doing it. And then they talk about what they are doing. They're using very sophisticated equipment called hyperspectral imaging, and they're also using NASA airplanes. So there's a big activity in the NASA airborne, okay, to support this thing. I watched this thing, looking at, and in my past days, I have also worked in oceanography a little bit, in physical oceanography. So I look at this and say, well, these guys are wonderful doing it. So can we do something different than what they're doing, and less cost and those type of things, using general aviation airplanes. Now, if you think about it, there are 600,000 pilots out there, licensed pilots in America, United States, 200,000 airplanes. A fraction of that, if we can use, just doing simple photography and IR imaging, infrared. So it is not by any means have a very sophisticated instrument, but all the instrument costs now hardly a few $100s. And then people fly for fun anyway.
This is the citizen science.
This is the citizen science. So citizen science is now a major effort in the entire federal government, whether you talk about FAA, the EPA, or you talk about NOAA, and NASA is on it too. So NASA's Office of Chief Scientist, okay, put together a proposal request. I submitted a proposal to do this thing. In 2014, when I was doing this, that's the first time I showed in the month of June and July the onset of these things, which later on in August shut down the water supply in the Toledo area, okay, for 4 days. Okay, so OCS saw that something that it could be innovative, it could be nice. So I got funded for that for this year in 2015-16. So that's what we are doing right now. Okay, and now a student Peter here is analyzing the data for using IR, infrared imaging, and so it is coming out really, really nicely so far.
You're involved in everything.
So it is no, not everything. I wish I could.
Oceanography.
Well, little bit.
You're a pilot.
Yeah. Thank you.
You've done a lot of agreements or partnerships. You talked about NIH, and how do you go about, or what gets started? How does someone who's looking to create a partnership, they're doing research, they're doing work, how do you go about doing that? That's one of the.
So that's an excellent question. I'm glad that you asked, because that really goes so beautifully well with this example. Now, this was about a few years back. And when I was doing this research, especially the cataract stuff, and then how I really got into it, the reason I really got into this research was because of my father, my dad. My dad developed cataract, okay. And when I heard about that, and I said, okay, well, he's developed cataract, no big deal. I come to work every day listening on the radio, and there is a laser that they shoot in the eye, they take the cataract away. So I went with him to an ophthalmologist's office, and the ophthalmologist said, no, there is no laser treatment. And I said, well, how do you remove it? He said, well, we call it phaco emulsification. We cut a little bit here and then take the lens out, and then we put a plastic lens in its place, and he will be fine. So my other question was then what happens inside? How do you develop a cataract? What is the scientific basis of it? And that point in time, he asked me if I'm a doctor, and I said no. I said, what do you do? Well, I work for NASA. And he said, so you're an engineer or whatever. I said, yeah, physicist, engineer. He said, well, don't worry about it. When you're going to get to his age, you will develop cataract as well. Okay. So I wanted to understand what was the scientific basis of this. So I spent 2 solid days on a weekend at Case Western's medical library, and I went through a lot of literature search and doing it. This is the time when the Google was not there, by the way.
Yeah.
Okay, so just coming in. So look at that. And I learned there are proteins responsible for aggregation, which could lead to cataract development. And at that time, I was doing some experiments for diagnosis of proteins for the experiments in protein crystal growth, and as well as in the colloids in the fluid physics area. So I said, well, we are already doing this thing, so what can we do in the eye? Okay, well, where do I go get the eye?
Right.
So I had asked some people. So they sent me to Sandusky, Ohio here to a slaughterhouse. I got some cow eyes, took it home, asked my daughter to dissect it for me.
You have your daughter dissecting
That's
cow
right.
eyes.
That's right. And then she was in high school
Family
at the time.
yeah.
And then I did not know what to expect.
Right.
So first time when I saw it, it looks a beautiful ball. Okay, this lens, bigger obviously than the human lens, but I saw. So my wife said, well, let's go have dinner, so just put this away. So I put it in a little jar and put in the fridge so they don't go away bad. Opened that fridge in about an hour later, and all of them were complete opacity. They were all opaque. So I said, wow, that's what a cataract is. Okay, so I put it on the shelf. An hour later, they all came back to normal. Okay, and that was a lucky shot, absolutely lucky shot. Okay, because after that, I repeated the experiment 3-4 times, and didn't happen. Right. Sometime it would, and sometime it would not. Right. So I'm saying something is I'm doing wrong or whatever. But anyway, so took the data from these devices that you see here, and then I started sharing this thing with ophthalmologists, some of them that I knew through some friends. One of them was in Philadelphia, Dr. Michael Della Vecchia at Bryn Mawr Hospital. Okay. So he said, well, you got something over here. This is really great. Okay. So I put this stuff in my Honda Civic hatchback at the time and drive to his clinic over there. And he knew Dr. Dubin, who was a veterinarian, and he would provide me the dogs and the rabbits and the cats, okay, because it's non-invasive. And then we would do it in there. And then we got a lot of nice data. We published a couple papers. And then NIH, National Eye Institute, Deputy Director Leon Elvine read an article, and he gave me a call. And he said, I'm very interested in this thing that you have done and published. Has anybody at NIH talked to you about this thing? Okay, well, why don't you get together? Okay. So I went and sat down with him. We talked about that, and the rest is obviously history. Yeah. But NASA over here was wonderful, okay, in promoting this stuff. And then they said, well, let's go do this in an agreement. So that was the first agreement that NASA we had here with NIH. Another one happened with FDA, okay? And that became a poster child, this agreement between NASA and NIH, which they speak very highly of it, okay, at NIH. And this became a really good example of 2 federal agencies working together.
Yeah, okay, oh, that's a great, I mean, it comes together, this notion that there's a problem, you know. It leads to an experiment, you experiment, you try things out, you share the knowledge broadly, you meet the people and they have ideas and you try things again, and then you get to a point where you can validate or you can test, and so it's a continuous kind of a thing. But it comes from your personal interest. So what work does your daughter do nowadays?
Oh, my daughter is now a neurologist.
Okay.
Yeah, she's
So it
a-
had an impact, by doing that research with you.
Oh, no, she won't tell you that.
That's
She will tell you it's very difficult to raise Indian parents. Okay.
So I knew we wouldn't cover things. I got all these things we haven't gone through. So we're down to, our final question. Is there something that you would like us to hear about? I was going to ask for your thoughts in terms of your career. What would you advise to other people to have the kind of joy you have in your career and the success from working with others, and if there's any tips there? But I wanted to give the opportunity if there's something important that we missed.
Well, I will say two things. Okay, the one thing is that when you talk about success and you ask about, well, you are successful, so I don't think that I'm really successful. I'm still
You look
working
really
and learning
happy.
a lot of things.
You seem really happy.
So I am happy, no
Okay.
doubt about it. Of course, I'm very happy, and I'd like to do more than
Yeah.
what I have done here. So thank you for your accolade. So this question was asked. I was reading a book to Wilbur Wright. Okay, he was a famous aviator.
Right.
And someone back then, when he was successful, asked that, how would you say, what advice will you give to young people? Okay, although I don't see too many young people here, but maybe somebody watching it on YouTube. Sorry, Kathy. This is what we will
Everyone
say.
does YouTube now.
Exactly.
It's all, yeah.
So
We have simulated laughter in the room. This is just you and I talking.
So therefore, Wilbur Wright said
Yeah.
the following, to this effect. I don't exactly know the exact quote, but he said, find a good father and a mother and go live in Ohio. So that worked for me, okay? The other thing I would say is the following, when you talk about personal thing. I am very strongly, I'm a proponent of in-house research, okay? There are tons of talented people in this place throughout NASA. That's what inspired me, okay, to learn from them. It is very important for any agency, for any institution, for any country, especially for us, who is the first country in the world as a spacefaring nation, okay, who have done missions to all over the planets in this, even though beyond our solar system, for us to continue in that direction and make sure that we continue to do in-house research and we do not go behind and other people can take over.
Getting involved, doing the hands-on work is
Absolutely.
vital.
That's what
I
I
have
would
one more final question. I know I'm getting the signs, but I have to. If you went back to school, to college or whatever, is there something you would study based on what you know now? Is there something you would study more of that you just from the standpoint if you're going back, something that you spend more time with in terms of learning about?
Yes, I think looking at that, I think I would keep exactly the same that I have done.
Yeah.
But I would go and get an MD degree,
Doctor. Okay.
medicine.
Right.
Okay, so that what I'm doing is also enhances the work in that direction.
Okay.
But there are several nice teachers so far in my life
Yeah.
that I'm okay with it. But if I would be young, I would definitely go do that.
Yes. Well, you probably have another 50 years.
Yeah,
Although
there we
you
go.
can look in your eyes and probably figure that out.
Right.
So anyway, it's been astounding. Love that we've run out of time, but it's gone very fast. You've given some wonderful demonstrations, and I think you've given an understanding of science that I think is counterintuitive about the working with others, about the collaboration, about the sharing of knowledge, about the experimentation, about the taking chances, and it's been just a pleasure to learn with you.
Thank
So
you very much.
Thank you for your time.
Thank you for
And
having me.
also want to thank the folks here at NASA Glenn Research Center, which is in Cleveland. And again, particularly want to thank our CKO here, Martin Forkosh, and Human Resources, Kathy Clark and Susan Snyder, for keeping us on track, and the folks who are filming. So thank you for your time, and hopefully you keep learning, staying curious. So thank you.
Thank you. Thank you very much.